Now we move from prompting to fine-tuning. In this chapter, we'll look at how models are adapted by changing their weights and why that matters in practice. Prompt-based methods steer a model with instructions, context, and tools. Fine-tuning goes deeper. Instead of only shaping the input, it updates the model's parameters so the behavior itself changes. Fine-tuning can sharpen domain performance, like coding or medical QA, and it can also improve safety. Most often, though, it is used to make the model follow instructions more reliably and produce specific styles or formats. Fine-tuning gives you more customization, but it also asks for more upfront work. A big question in this chapter is when fine-tuning is worth it and when a method like RAG is the better choice. Compared with prompt-based approaches, fine-tuning usually needs far more memory. At modern model sizes, even a naive attempt can exceed a single GPU, which is why memory efficiency becomes a central issue in this chapter. That pressure led to parameter-efficient fine-tuning, or PEFT. Instead of updating everything, PEFT changes only a small part of the model, and adapter-based methods are one of the most important families to understand. Once you enter fine-tuning, you're no longer just prompting a model, you're working with training. So some machine learning background becomes necessary, and this chapter will cover only the core ideas needed for the discussion. This is the most technical chapter in the book, mainly because the topic spans many ideas. If a section starts to feel too deep for your needs, it's completely reasonable to skip ahead and come back later. We've set the stage, so now we can start building the foundations. Next, we'll get into the concepts that make fine-tuning work. In this section, we'll build a clear picture of fine-tuning, what it is, why it helps, and the main ways it shows up in practice. The key idea is simple. Start with a capable base model, then adapt it to a specific task. Fine-tuning begins with a model that already knows something useful, but not everything you need. The goal is to shape that model so it performs well on your target task without starting from zero. Fine-tuning is one form of transfer learning, where knowledge from one task helps with another related task. You can think of it the way a musical skill carries over from one instrument to another. The learning is not identical, but it still gives you a head start. A classic example comes from multilingual translation. A model that knew Portuguese, English, and English-Spanish translation could generalize to Portuguese, Spanish, even without direct examples of that pair in training. This is why transfer learning became so important in deep learning. If the target task has little labeled data, you can first learn broad patterns from a larger source task and then adapt those patterns to the smaller problem. For large language models, pre-training on text completion creates a broad foundation. That knowledge can then be transferred to specialized tasks like legal question answering or text-to-SQL, where task-specific data is much scarcer. One major benefit is sample efficiency. The model learns the desired behavior from fewer examples. Instead of needing millions of labeled cases, a strong base model may only need a few hundred task examples to get useful performance. A useful way to think about fine-tuning is that it does not invent everything from scratch. Often, the model already has the capability, and fine-tuning mainly makes that capability easier to access and more reliable for users. Fine-tuning is not the only transfer learning strategy. There is also feature-based transfer, where a model produces embeddings or other features that a separate model uses downstream. In feature-based transfer, you reuse the model as a feature extractor rather than adapting all of its weights. A common pattern is to take those features and add a classifier head on top for the final task. This approach has long been popular in computer vision. People often reuse models trained on large image datasets to power tasks like detection or segmentation, where training data is more expensive. Now let's zoom in on fine-tuning as part of the full training pipeline. Anything you do after pre-training counts as fine-tuning, so it can include several different methods, including supervised and preference-based approaches. Pre-training usually relies on self-supervision, which means the model learns from unlabeled data. For language models, that often just means large collections of text sequences with no manual annotations. Before expensive labeled fine-tuning, you can often do a cheaper stage of self-supervised adaptation on raw domain text. For example, legal documents or Vietnamese text can teach the model domain vocabulary and style before instruction tuning begins. Supervised fine-tuning can train a model either to predict the next token or to fill in missing text. That second style, called infilling, is especially helpful for editing and debugging tasks, even if the original model was trained autoregressively. Self-supervised training gives the model broad knowledge, but that does not always match what users want. Supervised fine-tuning uses high-quality labeled examples to make the model more useful, more predictable, and better aligned with human preferences. The supervised setup is straightforward. Give the model an input and train it to produce the desired output. The input might be an instruction, and the output might be a summary, a label, or some other response, depending on the task. Another option is to fine-tune with reinforcement learning so the model favors responses people prefer. In that case, the training data usually compares a winning response against a losing one for the same instruction. Fine-tuning can also change how much text the model can handle at once. Long context fine-tuning is harder because it often requires architectural changes, and a model that works well on long inputs may lose some quality on shorter ones. This figure shows how different fine-tuning techniques were combined to produce code llama variants. The important takeaway is that long context fine-tuning can dramatically increase usable context length, which is essential for large code files. Fine-tuning is useful at two different stages. Model developers may do it before release, but application developers often choose among already post-trained models and adapt the one that best matches their needs. This diagram is meant to show the overall flow of fine-tuning choices. As you read it, focus on how a base model can be adapted in different ways rather than being retrained from scratch. This figure ties the section together by showing how one base model can lead to several specialized variants. It is a good visual summary of the idea that different fine-tuning methods produce different capabilities and context lengths. As an application developer, the less adaptation you need to do, the better. A more refined model with knowledge closer to your task usually means less fine-tuning work and faster progress to a useful application. Let's start by asking a practical question. When is fine-tuning actually worth it? This section explains how to judge that before you commit time, data, and compute. Fine-tuning is more expensive than prompt-based methods because it needs more data, more hardware, and usually more specialized ML support. In practice, you usually try prompting first and only move to fine-tuning after those experiments have been pushed as far as they can go. The two approaches can also work together, so in real projects, it is often not an either-or decision. Now, let's look at why fine-tuning matters. The main idea is simple. You use it when a model is close, but not quite right for the quality, format, or domain you need. Fine-tuning can improve both general performance and task-specific behavior. It is also a common way to make a model reliably produce structured outputs like JSON or YAML. A model can score well on broad benchmarks and still miss the details of your application. If it has not seen enough examples of your task, fine-tuning on your own data is often the fastest way to close that gap. This is a good example of domain adaptation. A model may handle standard SQL, but struggle with a less common dialect or with customer-specific query patterns. Fine-tuning on those examples teaches it the exact behavior you want. Fine-tuning is also used for bias mitigation. If a base model reflects harmful patterns from its training data, carefully curated fine-tuning data can push it toward fairer outputs and reduce those unwanted associations. Although you can fine-tune large models, smaller ones are much more common. They use less memory, are easier to train, and are cheaper and faster to deploy in production. A very common strategy is to teach a small model by using outputs from a larger one. That process transfers knowledge from the bigger model into the smaller one, and we call it distillation. Fine-tuning can make a small model outperform a much larger general-purpose model on a narrow task. The key point is that task-specific training data can matter more than raw model size when the target problem is well-defined. Fine-tuning has become more practical as strong open-source models have become widely available. That gives teams many more starting points, so adapting a model to a specific domain or workflow is now much easier. Before we jump into fine-tuning, it is worth asking when not to do it. In this section, we will look at the trade-offs, the hidden costs, and the cases where prompting or other approaches are enough. Fine-tuning can improve performance, but it is not the only way to get better results. Careful prompting and the right context can often solve the same problem, and structured outputs can sometimes be achieved with other techniques as well. A model tuned for one job may get worse at others. That matters when your application receives a mix of prompt types, because improving one path can unintentionally reduce overall usefulness. Here the model starts out decent at recommendations and feedback, but weak at order changes. If you fine-tune only on order change examples, you may fix that one weakness while degrading the other behaviors you still need. The first fix is to train on the full set of tasks you care about, not just the hardest one. If that still does not work well enough, you can use separate models for separate jobs or later merge them to simplify serving. For a new project, fine-tuning is usually a costly place to start. You need labeled data, and that data can be slow, expensive, or unreliable if you depend on open or synthetic sources. Fine-tuning is not just pressing a button. You still have to choose a base model, tune training settings, monitor learning, and diagnose problems like overfitting or underfitting. After training, you still need a deployment plan. That means deciding whether to host the model yourself or use an API, and making sure inference is practical for a large model in production. A fine-tuned model is not set and forget. New base models appear quickly, so you need a policy for monitoring, updating, and deciding when a newer model is worth switching to. Even when a newer model is better, the improvement may be too minor to justify the work. In practice, teams often prioritize projects that unlock new capabilities instead of chasing small gains. A good AI engineering workflow begins with prompting. Use the best prompting practices first, and only move to more advanced methods if careful prompt testing still leaves the task unsolved. Many teams blame prompting before they have really tested it. Once the instructions, examples, and metrics are cleaned up, the prompt often works well enough without any fine-tuning at all. In this section, we'll look at when domain-specific fine-tuning is actually worth it. The main question is not whether specialization helps, but whether it still beats strong general-purpose models. A common assumption is that you must fine-tune for every specialized task. But as general-purpose models improve, they often handle domain work surprisingly well, and sometimes outperform smaller specialized models. Bloomberg GPT is a useful early example of a domain model built for finance, especially for in-house use with sensitive data. It was expensive to train, which shows that specialization can require a major investment. But the comparison changed quickly. Research soon showed that GPT 4-0314 outperformed Bloomberg GPT on several financial benchmarks, which is a reminder that general models can be very strong even outside their original target domain. This table makes the point concrete. GPT-4 scores higher on both sentiment analysis and financial question answering. So the best domain model is not automatically the one trained only on domain data. More recently, several mid-sized models have reached near GPT-4 level performance, and some are open weight. That matters because self-hosting becomes possible, which is often important for privacy, control, and deployment constraints. Still, benchmarks are not the same as real production use. Bloomberg GPT may have fit Bloomberg's internal needs very well, and the training experience itself can build valuable expertise for future models. Before fine-tuning, it helps to run prompt experiments systematically. That process forces you to define evaluation, annotation rules, and experiment tracking, all of which carry directly into fine-tuning work. One classic reason to fine-tune is token efficiency. If you keep adding examples to prompts, cost and latency rise. Fine-tuning lets you bake those examples into the model and use much shorter prompts afterward. Prompt caching reduces that advantage because repeated prompt text can be reused. But fine-tuning still has one clear edge. You are not limited by context length in the same way, so you can train on many more examples than a prompt can hold. This diagram illustrates the basic trade-off, putting examples into every prompt versus moving that knowledge into the model itself. The key idea is that fine-tuning shifts repetition from inference time into training time. This figure reinforces the same message. If the same examples would otherwise be repeated in every request, fine-tuning can make the system simpler and cheaper to run at inference time. In this section, we'll compare two common ways to improve a model after prompting stops helping: retrieval and fine-tuning. The key question is whether the problem is missing information or the model's behavior. The next step depends on why the model is failing. If it lacks facts, retrieval helps. If it has the facts but responds poorly, fine-tuning may be the better fix. When the model is wrong because it does not know the needed information, RAG can supply the relevant sources at answer time. That is the right tool for factual gaps and stale knowledge. This is the simplest retrieval case. The model cannot answer well because the knowledge was never in its training context. The fix is not to change the model style, but to give it access to the missing material. Public models usually do not know your internal documents or organization-specific data. In that situation, the model may admit the gap, or it may confidently invent an answer. Another common failure is staleness. The model knows something, but its knowledge stops before the latest event or release. A question like this exposes the problem clearly. The model may give the old count because its training data ended before the newest album was released. Retrieval fixes this by bringing in current sources. This study found that for up-to-date questions, retrieval outperformed fine-tuning, and even base model plus RAG often beat fine-tuned variants. The lesson is that fine-tuning can improve a task, but can also make the model less broadly reliable. The table makes the pattern visible. Adding retrieval usually gives a large jump, while fine-tuning alone is weaker. When both are combined, performance can improve, but the base model with retrieval is still often the strongest baseline. Now, switch to behavior problems. If the answer is technically correct but not useful for the task, fine-tuning can teach the model what a good response should look like. Format failures are another fine-tuning case. If the model cannot reliably produce valid HTML or another structured output, more examples of that format during training can improve compliance. Semantic parsing is about converting language into a precise structure, like JSON. Common formats are usually manageable, but niche or complex syntaxes often need task-specific fine-tuning. A useful shortcut is this. Retrieval supplies facts, while fine-tuning teaches form, style, and syntax. High-quality fine-tuning data can help, but poor data can also make hallucinations worse. If you have both kinds of problems, begin with retrieval. It is usually simpler to deploy, and starting with a basic method like BM25 keeps the system easier to manage than jumping straight to embeddings. Retrieval can sometimes deliver a bigger gain than fine-tuning, especially on benchmarks that depend on knowledge recall. That makes it an efficient first upgrade when the issue is missing information. RAG and fine-tuning are not opposites. You can combine them, and sometimes retrieval on top of a fine-tuned model gives another boost, though not always compared with RAG alone. There is no universal path that fits every application. The right next step depends on your evaluation results and on which failure mode you're trying to reduce. This diagram shows a practical decision path. Start simple, measure the result, then move toward better retrieval or fine-tuning only when the evidence says you need it. Notice how the arrows represent choices based on observed failure modes. This figure summarizes the idea that application development is iterative. After basic retrieval, the next move could be more advanced retrieval or fine-tuning, depending on what your evaluation shows. Before you change the model, define how you will measure success. Evaluation is not a one-time step at the beginning. It should guide every improvement you try. First, establish a baseline and try prompting alone. That gives you the cleanest starting point for judging whether later changes really help. Use prompt engineering best practices and keep versions of your prompts so you can compare changes systematically. Often the simplest fix is still the best one. If prompting is not enough, the next low-cost step is to add examples directly to the prompt. Few-shot prompting can solve a surprising number of tasks before you need anything more complex. The number of examples can vary a lot by task. Some problems need just one or two examples, while others benefit from many more. If the model still misses important facts, the next step is retrieval. At that point, the issue is no longer prompt wording, it is access to knowledge. For information gaps, connect the model to relevant data sources and start with a simple retrieval method. Even basic term-based search can improve answers if it brings in the right context. After that, you decide whether to go deeper with retrieval or switch to fine-tuning. The next step depends on whether the remaining problem is knowledge or behavior. At this point, you reassess the failure mode. That tells you whether the application needs better retrieval, better output behavior, or both. If the model still lacks the right facts, move to more advanced retrieval methods. If it is already well informed, search for a different source of improvement. More advanced RAG methods, such as embedding-based retrieval, can improve how the system finds relevant information. This is the natural next step when simple retrieval is not enough. If the remaining issue is not knowledge but response quality, then fine-tuning becomes the stronger option. That usually means the model needs help with format, relevance, or safety. Fine-tuning is useful when outputs are irrelevant, malformed, or unsafe. It shifts the work from building a more complex inference pipeline to improving the model itself during development. Another possibility is to combine techniques rather than choosing just one. Once the simpler options plateau, hybrid approaches can be worth testing. Using both methods can unlock more performance than either one alone. Retrieval adds facts at answer time, and fine-tuning shapes how the model uses them. So the decision is practical. Start with prompting, then retrieval, then fine-tuning when the problem calls for it. With that foundation in place, the next topic is the biggest challenge in fine-tuning: memory. In this section, we'll look at why fine-tuning uses so much memory. Once you understand the bottleneck, the common optimization techniques will make a lot more sense. Fine-tuning can consume a lot of memory. So many methods are designed specifically to reduce that footprint. The key is to understand where the memory goes, because that tells you why each technique helps and which one fits your setup. We'll also build some simple formulas for estimating memory use by hand. Those quick calculations are useful when you want to figure out what hardware is needed to serve a model or fine-tune it. This part gets into lower-level machine learning and computing details, so it is more technical than the rest. If you already know these ideas, you can move through it quickly and focus on the memory formulas. Let's pull together the main ideas about why memory becomes such a challenge with large models. As we go through these takeaways, focus on the difference between inference and fine-tuning, because that is where the memory story changes the most. If this section feels dense, this is the summary to keep in mind. And if any of these points are unfamiliar, the rest of the section gives the background you need to make sense of them. First, I'm setting up the list of takeaways. The next points explain why memory matters so much and what specifically drives the cost up. With foundation models, memory is often the limiting factor both when you run the model and when you train it. Fine-tuning usually needs much more memory than inference because training has to store extra information for learning, not just produce outputs. Now we move from the general problem to the main causes. The next points show which model properties actually determine how much memory you need. Three things matter most here: the total number of parameters, how many of them are trainable, and how each number is represented. Those choices directly affect how much storage the model needs during fine-tuning. Next is the practical implication of that idea. If you can reduce the number of parameters that need updating, you can reduce the memory footprint too. The more parameters you train, the more memory you consume. That is exactly why parameter-efficient fine-tuning, or PEFT, exists. It aims to adapt a model while changing only a small subset of its weights. The next takeaway is about another lever you can use, changing how the numbers are stored. This is where quantization comes in. Quantization means representing values with fewer bits. That is a simple and very effective way to shrink memory use. For a 13 billion parameter model, moving from 32-bit to 16-bit storage cuts the weight memory roughly in half, from 52 gigabytes to 26 gigabytes. So far, the theme has been reducing memory cost. The next 2 points explain how precision choices differ between inference and training. At inference time, models are often run in lower precision to save memory and speed things up. Common choices include 16-bit, 8-bit, and even 4-bit representations. Training is a little different because the optimization process is more sensitive to numerical error. That means you cannot push precision down as aggressively. Training usually relies on mixed precision, where some operations stay in higher precision and others use lower precision. This balances stability and efficiency, which is why training precision is harder to reduce than inference precision. In this section, we'll connect training mechanics to memory use. The key idea is that only trainable parameters need the extra state that backpropagation uses, so the number of trainable parameters strongly affects fine-tuning cost. A trainable parameter can change during fine-tuning, while a frozen parameter stays fixed. That distinction matters because inference updates nothing, pre-training updates everything, and fine-tuning usually updates only part of the model. Neural networks are typically trained with backpropagation. Each step has a forward pass to compute predictions, then a backward pass to figure out how to improve the model. First, we'll look at the forward pass. This is the part where the model processes the input and produces an output. The forward pass just means moving from input to output. No learning happens yet. The model is simply making a prediction. Next comes the backward pass, which is where learning happens. The model uses the error signal to decide how each parameter should change. In the backward pass, the model updates its weights using the signals produced during the forward pass. This is the core step that turns an error into improvement. At inference time, we only need the forward pass because we're not training the model. During training, both passes run so the model can learn from its mistakes. The backward pass starts by measuring the mistake. That gives us a number we can optimize. We compare the model's prediction with the expected answer, called the ground truth. Their difference is the loss, and that loss tells us how wrong the model was. Once we know the loss, we can trace how the error came from each trainable parameter. For each trainable parameter, we compute a gradient, which tells us how strongly that parameter affects the loss. A larger gradient means that parameters should change more during the update. Finally, the optimizer uses those gradients to make the actual update. The optimizer decides how to adjust the parameters based on their gradients. SGD and Atom are common choices, and for transformer models, Atom is especially widely used. This example network is just a simplified visual aid. The goal is to make it easier to see how values move through the forward pass and how gradients flow back through the model. Notice the two directions in the diagram. Data flows forward to produce an output, then information flows backward to compute updates. That contrast is the whole logic of training. This figure ties the steps together in one small network. Keep an eye on how the same model produces predictions in one direction and learning signals in the other. During the backward pass, each trainable parameter needs extra information, its gradient and optimizer state. So as the number of trainable parameters grows, memory use grows with it. In this section, we'll estimate how much memory a model needs. The goal is to make hardware planning practical, so you can tell whether a model will fit before you try to run it. This matters in both directions. Sometimes you pick hardware for a model, and sometimes you already have hardware and need to check if the model will fit. A simple estimate can save you from choosing a chip that is too small. Real memory use depends on the workload and on optimization tricks like quantization or checkpointing. Since we can't account for every case, I'll focus on rough formulas that give you a useful estimate. Before we get into the formulas, keep one thing in mind. Inference and training stress memory in different ways. That difference is a big reason why training chips and inference chips often look very different. Inference and training do not use memory in the same way, and that affects chip design. We'll use that distinction to build separate estimates for each setting. First, let's look at inference. During inference, the model only runs the forward pass, so the main cost of the weights plus the temporary values needed while the model is generating output. If the model has n parameters and each parameter takes m bytes, then the weights alone take n times m bytes. That is the base memory cost before we add anything for activations or attention state. This is the core inference formula for the model weights. It tells you how parameter count and precision combine into a raw memory requirement. Inference also needs memory for activations, and for transformers, key-value vectors used by attention. Both costs grow with sequence length and batch size, so longer context or bigger batches use more memory. A common shortcut is to treat those extra inference costs as about 20% of the weight memory. It is only an estimate, and it becomes less accurate as context length or batch size increases. So the quick inference estimate becomes the weight memory times 1.2. That gives you a fast way to check whether a model will fit on a given device. For a 13 billion parameter model at 2 bytes per parameter, the weights alone take 26 gigabytes. After adding the 20% overhead, the total inference memory is about 31.2 gigabytes. This is why large models become hard to serve. A 70 billion parameter model at 2 bytes per parameter already needs 140 gigabytes just for the weights, before any extra runtime memory is added. Training is more demanding than inference. In addition to the forward pass memory, you also need space for gradients and optimizer state, and those costs scale with the number of trainable parameters. When you train, you keep the weights and activations, but you also store gradient information and optimizer state. That is why training usually needs much more memory than inference. We can summarize training memory with a simple breakdown. The total is the sum of weights, activations, gradients, and optimizer states. This separator just signals that the next line is the actual formula. We are moving from the idea to the concrete components. This is the training memory budget in one line. It reminds you that training is not just inference plus a little extra. It adds persistent state for learning. There is one more detail that matters when estimating training memory. The exact optimizer you use can change how much extra state you need per parameter. During backpropagation, every trainable parameter needs a gradient value, and some optimizers also keep 1 or 2 extra state values. So the memory overhead depends on the optimizer choice. The bullet style here just introduces the optimizer examples that follow. Each one shows a different amount of state. plain stochastic gradient descent is the simplest case. It keeps no extra optimizer state beyond the gradient itself. Next comes momentum, which adds a small amount of persistent state. That extra value helps smooth updates over time. A momentum optimizer stores one extra value for each trainable parameter. That gives it memory overhead, but still less than more complex optimizers. Now we move to the most common heavier optimizer. This one keeps two state values per parameter. Atom stores two optimizer values for every trainable parameter, combined with the gradient. That is why its memory cost is higher than SGED or momentum. For a 13 billion parameter model trained with Atom, you have one gradient plus two optimizer states per parameter. If each value takes 2 bytes, the total for gradients and optimizer state becomes very large. This calculation shows the scale directly. 3 stored values per parameter times 2 bytes each gives 78 gigabytes. Notice that this is only for gradients and optimizer states, not the full training footprint. If only 1 billion parameters are trainable, the memory drops proportionally. The formula is the same, but now the total is much more manageable. With 1 billion trainable parameters, the same atom-style calculation gives 6 gigabytes. This is why fine-tuning a smaller subset of parameters is so much easier on memory. One important caveat is that activations can be much larger than the simple estimate suggests. If you keep them for backward computation, they may end up using more memory than the weights themselves. A common way to reduce activation memory is to recompute them instead of storing them all. This is called gradient checkpointing, and it saves memory at the cost of extra compute time. This figure is meant to show how activation memory can outgrow weight memory at scale. The key takeaway is not the exact curve, but the shape of the problem. Activations can become the dominant cost. This caption reinforces the main lesson from the figure. As models grow, activation memory can become much larger than the memory for the weights, which is why memory-saving techniques matter so much. Let's look at how numbers are stored in memory, because that choice has a direct effect on model size. The key idea is simple. Fewer bits per value means a smaller memory footprint. Up to now, we've been assuming each value takes 2 bytes. That assumption matters because the storage cost of every weight adds up across the whole model. So cutting the cost per value in half cuts the model's memory in half too. Before we reduce memory, we need to understand the formats themselves. Neural networks usually store numbers as floating point values, and the FP family follows the IEEE 754 standard. We'll start with the common floating point formats and compare how many bits they use. FP32 is the common 32-bit floating point format. It's also called single precision, and it uses 4 bytes for each number. Next is the larger 64-bit format, which gives you more room but uses more memory. FP64 uses 8 bytes per value and is called double precision. It is useful in some scientific computing, but it is expensive for large neural networks. Now, let's move to a smaller format that is often used to save memory. FP16 uses only 2 bytes per value, so it can cut memory use substantially. This is why half precision is attractive in deep learning. FP64 is still common in tools like NumPy and Pandas, but neural networks usually prefer FP32 or FP16 because they are more memory efficient. In AI workloads, you'll also see BF16 and TF32, which are designed to fit modern accelerator hardware better. Numbers do not have to be stored as floats. Integer formats, such as int8 and int4, are becoming more popular, especially when memory savings are important. Most floating point formats dedicate 1 bit to the sign. The remaining bits are split between range and precision, and that trade-off is what controls how the format behaves. Range is about how large or small a value the format can represent. More range bits usually means the format can handle a wider spread of numbers. Think of range as the span of numbers you can cover. If the format has more bits for range, it can represent much larger and much smaller values without overflowing. Precision is about how finely a number can be represented. Now we're talking about how much detail survives when a value is stored. If a format has fewer precision bits, the value becomes less exact. A number like 10.1234 might be rounded to 10.12, which is close but not identical. This figure compares several floating point formats and shows the balance between range and precision. It helps you see that changing the bit budget always comes with a trade-off. Notice how the formats are arranged to highlight their different bit allocations. The important takeaway is not the exact graphic labels, but the relationship between total size, range, and precision. This figure is the visual summary of the formats we just discussed. Use it as a reference for comparing how much range and precision each format gives you. In general, formats with more bits are more precise. If you convert a value from FP32 to FP16 or BF16, you save memory, but you may also change the number slightly or introduce error. The table below shows examples of what happens when FP32 values are converted into smaller formats. Keep an eye on where the last digits change because that is where precision is being lost. Here, the table begins the actual numeric examples, so we can see the effects of conversion rather than just talk about them abstractly. These rows show that smaller formats often round the value, and in some cases they cannot represent the number exactly at all. As the values get larger, the lower precision formats start to lose more detail. This is the extreme case. If a value is too large for FP16, it becomes infinity. That is a hard limit, not just a small rounding error. BF16 and FP16 use the same total number of bits, but BF16 spends more of them on range and fewer on precision. That means BF16 can keep larger values, while FP16 can sometimes be a little more exact on smaller ones. This is an important practical warning. Using the wrong numerical format can silently change a model's behavior, even if the model loads without an obvious error. Always load a model in the precision it was trained or released for. A mismatch can damage quality dramatically, and the Llama 2 example showed that even experienced teams can be caught by this mistake. The right format depends on three things: the range of values in your workload, how sensitive it is to small numerical changes and the hardware you are running on. In practice, format choice is always a balance between memory, accuracy, and speed. In this section, we'll look at quantization, the idea of using fewer bits to store a model's values. That simple change can cut memory use dramatically without changing the model itself. When you reduce precision, each weight takes less space, so the whole model becomes smaller in memory. For example, a 10 billion parameter model drops from about 40 gigabytes at 32-bit precision to about 20 gigabytes at 16-bit precision. The key point is that quantization is a simple, widely useful way to make models cheaper to store and run. In this section, we'll clean up the terminology around quantization and then look at what happens. The main theme is simple: reduce precision where it helps, but choose the method based on memory, speed, and accuracy trade-offs. Strictly speaking, quantization means mapping values into integers. But in practice, people use the word more broadly to include many kinds of precision reduction. I'll follow that broader usage here, because that matches how the literature usually talks about it. Two questions drive any quantization strategy: what part of the model should be reduced, and at what stage should that happen? Those choices determine both the memory savings and the risk to model quality. First, let's isolate the target. In practice, you usually choose the biggest memory hogs, but only if they can be reduced without too much accuracy loss. During inference, the main memory costs usually come from weights and activations. Weight quantization is more common because it tends to be easier to apply and usually causes less accuracy damage than activation quantization. The next choice is timing. Quantization can be done while training is happening or after training is finished. Post-training quantization means you train the model normally first, then compress it afterward. That is the most common setup, especially for people building applications rather than training models from scratch. Now we move from the general idea to the most common use case: running models efficiently at inference time. This is where reduced precision has become standard practice. Early deep learning systems usually trained and serve in 32-bit floating point. More recently, serving in 16-bit and lower precision has become common, and modern LLM work has pushed all the way to 8-bit and 4-bit methods. Mixed precision is a practical compromise. Use low precision where it is safe, and keep higher precision where the model needs it. That idea shows up in modern device-side inference and in new hardware designs built for 4-bit computation. Once you get below 8 bits, the representation itself becomes a major issue. You can still use floating point style formats like FP8 or FP4, but many systems switch to integer formats such as INT8 or INT4. Quantization can go very far, but not infinitely far. In the extreme, researchers have explored 1-bit representations, where weights are reduced to the smallest possible binary form. BitNet B1.58 is a striking example. It uses about 1.58 bits per parameter and still reaches performance close to a 16-bit Llama 2 at several model sizes. The point is not that precision no longer matters, but that clever design can preserve quality at very low bit rates. This table makes the trade-off visible. BitNet is slightly behind in some benchmarks, ahead in others, and overall it stays surprisingly competitive while using far less precision. Lower precision helps in two ways. It reduces memory, and it can make computation faster. That said, the real speed up depends on hardware and on whether conversion overhead cancels part of the game. The downside is accuracy risk. Every conversion can introduce small errors, and if values exceed the representable range, the result can become infinity or some other bad approximation. That is why precision reduction is still an active research problem. Today, a common workflow is to train in higher precision and then reduce precision for inference. Major ML frameworks support that pattern directly, so PTQ is often only a few lines of code away. This matters even more on edge devices, where the hardware may only support quantized execution. That is why mobile and embedded inference toolkits also expose post-training quantization. So far, we've focused on inference. Now, let's look at quantization during training, which is less common but increasingly important. Training time quantization usually serves one of two goals: better low-precision inference later, or lower training cost right now. Sometimes it helps with both. The first goal is to make the model robust to low precision so it performs well after deployment. This addresses the accuracy drop that can happen when you quantize only after training. In other words, the model learns under the same constraints it will face later. That makes post-training quantization less risky. The second goal is cost reduction during training itself. Quantization can shrink memory use and speed up computation, which means cheaper hardware or larger models on the same hardware. So quantization is not just a deployment trick. It can also be a training efficiency tool, especially when compute budgets are tight. A single quantization method may target inference quality, training efficiency, or both. The key is to be clear about which objective you are optimizing. Quantization-aware training, or QAT, keeps the computation in high precision but injects low-precision behavior during training. That helps the model adapt, although it does not usually make training faster and can even slow it down. Training directly in low precision can improve both inference readiness and training efficiency, but it is harder to stabilize. Gradients are especially sensitive, so the optimization problem becomes more delicate. A common compromise is mixed precision. Keep a high-precision copy of the weights, but store gradients, activations, or other less sensitive values in lower precision. Some methods even mix precisions within the same model, keeping the most sensitive parts at 16 bits. Frameworks often help here with automatic mixed precision, or AMP. That lets the system choose which operations can safely run in lower precision. There's also a practical workflow split. Pre-train in higher precision when compute is available, then fine-tune in lower precision later. This makes quantization useful not just for large labs, but also for teams working with limited compute. In this section, we'll look at ways to make fine-tuning more practical and less memory-hungry. We'll start with parameter-efficient methods, then move into model merging, which gives us another way to build custom models. Large models are expensive to fine-tune because training needs a lot of memory. If we can reduce that footprint, more people can afford to adapt these models to their own tasks and data. That is why this section focuses on parameter-efficient fine-tuning. We'll also cover model merging, which is related but not quite the same as fine-tuning. Instead of adapting one model in place, merging combines several models, often fine-tuned ones, into a single model for a shared goal. This area is especially interesting because newer models and newer fine-tuning methods have led to many inventive merging strategies. So beyond the core techniques, there is also a lot of room for experimentation. In this section, we'll look at why full fine-tuning is often too expensive and how parameter-efficient methods solve that problem. The key idea is to get close to full model performance while updating far fewer parameters. Early on, models were small enough that people could simply update the whole model. That is full fine-tuning. Every parameter is trainable, just like in training, except you start from pre-trained weights instead of random ones. So the difference from training is not the optimization process itself. It's the starting point. Fine-tuning begins with a model that already knows useful patterns and then adapts that knowledge to a new task. Once models became large, memory became the bottleneck. The bigger the set of trainable parameters, the more GPU memory you need, so a 7B model already pushes the limits of common hardware. We'll break the estimate into pieces so the memory cost is easy to see. First comes the weights themselves, then the optimizer state, and finally the total. If the model weights are stored in FP16, the weights alone take 14 gigabytes. That is already a substantial chunk of a consumer GPU's memory budget. The weights are only part of the story. Training also needs gradients and optimizer state, which can easily dominate the memory footprint. With Atom, the optimizer adds a lot more memory because it stores extra moments for every parameter. For a 7B model in 16-bit precision, that adds about 42 gigabytes. Now we combine the pieces. This is where full fine-tuning starts to become impractical on ordinary hardware. Add the weights, and optimizer stay together, and you get 56 gigabytes. That number is enough to show why full fine-tuning is often out of reach for a single consumer GPU. Most consumer GPUs have far less memory than that, and we still haven't counted activations. So even before we talk about data, full fine-tuning can simply be too expensive to run. This note gives the broader strategy. If a model does not fit, you can shrink the memory footprint or use hardware more efficiently. And PEFT is one of the main ways to do the first. There are two broad approaches here. Some methods reduce how much memory the model needs, like quantization and PEFT, while others spread the load across devices, such as CPU offloading. Data is the other constraint. Full fine-tuning usually needs a lot of high-quality labeled examples, so people move to partial fine-tuning, where only some layers are updated and the rest are frozen. Even though partial fine-tuning saves memory, it often needs many trainable parameters to match full fine-tuning. That is why it is called parameter inefficient. You still pay a large cost for modest gains. This plot shows the trade-off clearly. As you increase the number of trainable parameters, performance improves, but you need a surprisingly large fraction of the model before you get close to full fine-tuning. The figure makes the same point visually. Partial fine-tuning climbs slowly toward full fine-tuning, so the gap closes only after updating a lot of parameters. That is the motivation for parameter-efficient methods. Parameter-efficient fine-tuning asks a very specific question. Can we get near full fine-tuning performance while training far fewer parameters? In practice, that usually means using several orders of magnitude fewer trainable weights. Halsby and colleagues introduced PEFT by showing that you can insert new parameters into a pre-trained model at the right locations and still get strong results. Their adapter approach is one of the earliest and most influential examples. This diagram shows the basic idea. Small adapter modules are inserted into each transformer layer. The base model stays fixed, and the new modules become the only trainable part. So the adapter strategy is simple but powerful. Keep the pre-trained backbone intact and train a lightweight add-on. That gives you strong adaptation without touching most of the original model. During fine-tuning, the original weights remain frozen and only the adapters move. The result is impressive, near full fine-tuning performance on GLUE, with only a tiny fraction of the trainable parameters. There's a trade-off, though. Because adapters add extra layers, the model has more work to do at inference time, so serving can be slower. That trade-off is still attractive because PEFT makes fine-tuning accessible on much cheaper hardware. It can also work well with far less labeled data than full fine-tuning often requires. So now we have the big picture. Next, we'll look at the main families of PEFT methods and then focus on the most widely used one, LoRA. PEFT is not one single technique. It's a family of approaches, and the first useful split is between methods that add parameters and methods that change the input representation. Most PEFT methods fall into two broad groups, adapter-based methods and soft prompt-based methods. That's a helpful mental model, even though new variants keep appearing. Adapter-based methods add trainable modules directly into the network, so they are sometimes called additive methods. The key idea is that the base model stays mostly unchanged. Among adapter methods, LoRa has become the most popular by far. Other variants like BitFit, IA3, and long LoRA explore different ways to get similar benefits under different constraints. Soft prompt methods take a different route. Instead of adding layers, they add trainable tokens that are fed into the model along with the prompt. The next 2 points explain why soft prompts are unlike ordinary prompts. One difference is how they are represented, and the other is whether they can be trained. Hard prompts are human-readable words or tokens. Soft prompts are learned embeddings, so you cannot read them like normal text, even though they steer the model's behavior. The representation difference matters because it changes what can be optimized. Soft prompts are numerical objects, not text strings. Hard prompts stay fixed, but soft prompts are updated with backpropagation. That makes them a bridge between prompt engineering and fine-tuning. You can combine soft prompts with normal prompts to guide the model more precisely. The figure shows that this is not an either-or choice. The two can work together. Notice how the model receives both ordinary prompt text and learned prompt vectors. That combination is what makes soft prompting feel like a blend of prompt engineering and fine-tuning. This figure reinforces the main idea. Soft prompts are trainable input-side additions, and they can sit alongside hard prompts. That gives you another way to adapt behavior without changing the whole model. Soft prompting has several closely related variants, and the main difference is where the soft tokens are inserted. Some prepend them at every layer, while others only add them to the input embedding stage. To see what people actually use, the author looked at issues in the Hugging Face PEFT repository as a rough popularity signal. It's not a perfect measure, but it gives a practical snapshot of what the community asks about most. This chart is a proxy for adoption. The tallest bars suggest which methods generate the most questions and discussion in practice, which often tracks real-world usage. The takeaway from the chart is simple. LoRA stands out as the most popular choice. Soft prompts are less common, but they remain attractive when you want more control without full fine-tuning. So the field has a clear center of gravity. LoRA is the default for many users, while soft prompts serve people who want something between pure prompting and full fine-tuning. That is why the next section zooms in on LoRA. Even if you later use a different PFT method, understanding LoRA gives you a useful framework for how efficient fine-tuning works. Now we move from the general idea of PFT to its most important example. LoRA is the method you will see most often in practice, so it is worth understanding carefully. LoRA improves on early adapters by avoiding extra inference cost. It adds small trainable components that can later be merged back into the base weights. Instead of training a whole matrix, LoRA trains a low-rank update. The update is represented by two smaller matrices whose product has the same shape as the original weight matrix. Let's describe the process step by step. We begin with a normal weight matrix, and then replace its update with a lower rank approximation. First, we choose a rank for the approximation. That rank controls how much capacity the LoRa update will have. We build two smaller matrices, A and B, whose product matches the shape of the original weight matrix. The rank R is the key hyperparameter because it determines both parameter count and flexibility. Next, we add that lowering product back onto the original matrix. This gives the model a learnable adjustment without replacing the base weights. The scaling factor alpha controls how strongly the LoRa update contributes when matrices are merged. The important idea is that the base weight stays, and the LoRa term acts as a small learn correction. Finally, only the small LoRa matrices are trained. The original weight matrix remains frozen throughout fine-tuning. That is the real efficiency gain. The model learns by updating A and B, not the full matrix W. So the trainable part becomes much smaller than full fine-tuning. The figure shows the full flow visually. Once you see the freeze and update pattern, the LoRa mechanism becomes much easier to remember. Here the diagram emphasizes the structure of LoRa. A large matrix is replaced by a low-rank pair. During fine-tuning, only those smaller matrices are updated, which is why the method is so memory efficient. So the core recipe is simple. Decompose, train the small pieces, and keep the base model intact. That combination is what makes LoRa practical at scale. This note connects LoRa to an older idea, low-rank factorization. The math is not new, but LoRa applies it in a way that is especially useful for fine-tuning large models. A large matrix can often be approximated by two much smaller matrices. That cuts the parameter count dramatically, and with it, the compute and memory required. The rank tells us how much information the factorization can preserve. A lower rank approximation is cheaper, but it is also less expressive than the full matrix. That is the key trade-off. More rank means a better approximation, but also more parameters, so the efficiency advantage shrinks as the rank rises. Because of that factorization, LoRa can be extremely compact and still work well. In large models, it can match or even beat full fine-tuning on some tasks with only a tiny number of trainable parameters. At this point, a natural question appears. Why should such a small update be enough? The answer points to how pre-trained models organize information internally. This is the surprising part. If a model needed many parameters to learn a behavior from scratch, why can it change that behavior with so few during fine-tuning? The same question applies to data. Pre-training may require enormous data sets, but fine-tuning often needs only a small labeled set, so something about the model has already been compressed or organized. One explanation is intrinsic dimension. The idea is that pre-training pushes the model into a compact representation, so downstream tasks can be learned with far fewer degrees of freedom. That leads to a follow-up question. If low-rank methods help fine-tuning, why not use them from the start during pre-training? In principle, that could reduce training cost even more. Researchers have explored low-rank neural networks for years. The challenge is not whether they can save parameters at small scales, but whether they can scale cleanly to large language models. At smaller scales, the pattern is clear. Factorization can be very effective. SqueezeNet is a classic example of getting strong accuracy with far fewer parameters than a larger baseline. More recent work has tried to bring this idea to larger language models. LoRA and QLoRA are examples of low-rank training methods that show promising results at billion-parameter scale. The open question is how much full-rank learning is needed before low-rank methods can take over. That balance between compression and expressivity is still an active research topic. Now that the mechanism is clear, we can ask how to configure in practice. The two main choices are which matrices to adapt and what rank to use. Applying LoRA is not just one decision. You have to choose both the target weight matrices and the factorization rank, and those choices determine the quality-cost trade-off. Because LoRA is applied to specific weight matrices, the model architecture matters a lot. Different architectures expose different matrices, so the same LoRA setup may not transfer directly. In transformers, LoRA is most often applied to the attention projections, query, key, value, and output. That is where many implementations focus first. A common practice is to apply the same LoRA choice to every matrix of a given type. That keeps the setup simple and consistent across layers. If your memory budget is fixed, the real question is how to spend it for the best gain. You usually cannot adapt everything, so you want the most useful matrices first. The original GPT-3 LoRA study used a strict budget of 18 million trainable parameters. That constraint forces you to think carefully about which matrices deserve the rank allocation. Let's break down the options they tested. The goal is to see how to distribute a limited parameter budget across the attention matrices. One option is to spend the budget on a single matrix and give it more rank. That concentrates capacity in one place. Another option is to spread the budget across more matrices. This usually lowers the rank per matrix but broadens coverage. Here the budget is split between two matrices. You get less rank per matrix, but more parts of the attention block can adapt. A third strategy is to cover all four attention matrices with a very small rank each. That makes the adaptation more distributed. This is the most distributed option in the experiment. Even though each matrix gets only a small rank, the combined coverage can perform very well. This note shows the arithmetic behind that budget. It helps explain why a small rank can still cover a large transformer when the model is big enough. With GPT-3 size, even rank 2 across all four attention matrices adds up to only about 18.9 million trainable parameters. That is tiny compared with 175 billion total parameters. In that study, adapting all four attention matrices with rank 2 gave the best results on the tested benchmarks. If you can only choose two, query and value were the strongest pair. The table summarizes the trade-off. Different matrix choices give different results even under the same budget. It is a good reminder that parameter allocation matters as much as parameter count. Later work suggests that extending LoRa beyond attention layers can improve performance further. In particular, feed-forward layers can contribute important gains when memory allows. A useful practical rule is that small ranks are often sufficient. In many cases, A rank somewhere between 4 and 64 gives most of the benefit without much memory cost. More rank does not automatically mean better performance. Sometimes it helps, but sometimes it gives no gain or even overfits, so the best choice still depends on the task. The other important hyperparameter is alpha, which controls the strength of the LoRa update. In practice, you choose alpha and R together because the best scale depends on both the task and the model. Next, we move from training to deployment. LoRa has a big serving advantage because its modular adapters can be merged or swapped depending on the use case. LoRa is not only cheaper to train, it also makes serving more flexible. The same base model can be reused, and the adapter decides how that base model behaves for a task. There are two main ways to serve a LoRa model. One minimizes inference cost, and the other is better when you need to switch among many adapters. First, let's look at the simplest deployment path. It favors speed at inference time. You can merge the LoRa weights into the base model ahead of time. Then inference runs like a normal model, with no extra latency from the adapter math. The second approach keeps the adapters separate. That makes the model easier to swap, even if it adds some overhead during inference. Here, the merge happens on the fly during inference. That costs some time, but lets you manage many adapters without rebuilding the whole model each time. If you only serve one adapter, merging is usually best. If you serve many tasks, keeping adapters separate saves a lot of storage because all of them can share the same base matrix. This flowchart shows the multi-LoRa setup. The key thing to notice is that one base model can support many task-specific adapters, which makes deployment much more modular. That reuse is the main reason multi-LoRa serving is attractive. You trade a bit of runtime overhead for much simpler storage and task switching. Imagine one model shared by many customers. With merged weights, you would store a full copy for each customer, but with separate adapters, you store one base model and many tiny add-ons instead. A large matrix has millions of parameters, but a rank 8 LoRa update is tiny by comparison. That huge gap is why adapter storage stays manageable even when the base model is large. Now we compare the two storage strategies directly. The difference gets dramatic once you multiply by many customers or tasks. If you store a full merged matrix for each of 100 customers, the total parameter count explodes. That is the cost of treating every fine-tuned model as a separate full model. The second option keeps the shared base and only adds small customer-specific adapters. That is where the storage savings come from. With one shared matrix and 100 small LoRa adapters, the total stays much smaller. That is why multi-LoRa serving is a practical deployment strategy. This setup also makes switching tasks faster. Instead of loading a whole new model, you just load the adapter for the target customer or task. That modularity is powerful for product teams. You can keep one compact base model and attach multiple specialized adapters, even on device, when combined with quantization. Another advantage is reuse. Because adapters are portable, people can share fine-tuned LoRa weights the same way they share pre-trained models. LoRa is not perfect. It may underperform full fine-tuning, and it can be harder to implement for less common base models, although popular frameworks hide much of that complexity. Next, we push the efficiency idea even further. Quantized LoRa reduces memory by compressing the base model itself, not just the adapter. Many LoRa variants try to shrink the adapter even more, but the adapter is already small compared with the full model. So the bigger wins usually come from reducing the model weights instead. This table shows the scale difference clearly. The LoRa parameters take only megabytes, while the model weights take gigabytes, so the base model dominates memory use. That is why quantized fine-tuning is so useful. Rather than shrinking LoRa further, methods like QLoRA compress the weights, activations, or gradients to save much more memory. QLoRA stores the base weights in 4-bit and F4 format, then dequantizes them to BF16 during computation. It also uses paged optimizers to handle memory spikes, which lets very large models fit on a single GPU. The result was a family of fine-tuned models called Guanaco. They were strong enough to compete well on public benchmarks and even compare favorably in human-style preference evaluations. This table compares yellow ratings judged by GPT-4. It shows that QLoRA style fine-tuning produced models that were surprisingly competitive for their size and hardware budget. The downside is that quantization is computationally expensive. So QLoRA reduces memory dramatically, but it can slow training because of the extra quantize and dequantize work. That trade-off has made quantized LoRA an active research area. QLoRA is the best-known example, but several newer variants are trying to push the efficiency further. In this section, we'll look at a different way to build custom models, combining models instead of only modifying one. The key idea is that merging can help with multitask learning, deployment, and memory efficiency. Fine-tuning changes a single model, but model merging starts with two or more models and combines them into a new one. That gives you more flexibility because you can merge models after fine-tuning them separately, or even merge first and fine-tune later. A useful practical advantage is that simple merging can often be done without a GPU. That makes it attractive when you have limited compute, although you may still fine-tune the merged result afterward to improve quality. The goal is to produce a single model that does more than the separate models did on their own. Sometimes that means better accuracy on a task, where each model covers different strengths and the merged model captures more of them. Merging can also reduce the number of parameters you need to serve, which lowers memory use and deployment cost. This is especially useful with adapter-based models, where multiple adapters trained from the same base model can sometimes be combined into one. A major use case for merging is multitask fine-tuning. Instead of forcing one model to learn every task at once, you can train separate task-specific versions and then combine them afterward. The first option is to train on a dataset that mixes all tasks together. It is simple in concept, but learning multiple skills at once usually needs more data and more training. Here the model sees examples from every task during the same training run. The trade-off is that multitask learning is harder, so the model often needs more examples and more optimization to perform well. The second option is to train on one task, then move to the next. That is often easier to set up, but it has a serious drawback. The model may overwrite what it learned before. This overwrite problem is called catastrophic forgetting. A model can become better at the new task while losing performance on the earlier ones, which makes sequential training risky for multitask setups. Model merging gives you a third path. Fine-tune each task separately, in parallel, and combine the results afterward. That usually helps each task learn better, while also avoiding the main forgetting problem from sequential training. This is also valuable for on-device deployment, where memory is tight. Instead of keeping several specialist models on the device, you can merge them into one model that handles multiple tasks more efficiently. On-device models are useful when data must stay local, when internet access is unreliable, or when you want to cut cloud inference costs. The more work the device can do itself, the less you rely on data centers. Model merging also fits naturally with federated learning. Different devices can keep learning from their own data, and later their updated models can be merged into a single improved base model. The broader idea comes from ensembling, combining multiple models to get better performance than any one model alone. The difference is that ensembles usually combine outputs, while merging combines parameters. In an ensemble, you might run several models on the same query and then vote or combine their answers. That can improve accuracy, but it costs more at inference time because every request has to be processed by multiple models. This figure highlights the contrast. Ensembling keeps models separate, while merging folds them into one model. That is one reason merged models are so attractive for modern leaderboards and practical deployment. Notice the difference in workflow. With ensembling, several models stay intact and their outputs are combined. With merging, the models contribute to one new set of parameters. Use this figure as the mental model for the rest of the section. It shows why merging is cheaper to serve, even though ensembling is often easier to reason about. Many merging methods are still evolving, so the details can change quickly. I'll focus on the main ideas rather than any one recipe, because the high-level patterns are more stable than individual papers. At a high level, merging usually happens in three ways: summing parameters, stacking layers, or concatenating components. The details differ, but these three patterns cover most of the common intuition. This diagram shows the three merging styles side by side. Keep the picture in mind. One method blends values, one reuses layers and sequence, and one appends components together. We're about to unpack each of these methods one by one. First, we'll look at summing, because it is the simplest and most widely used starting point. These approaches are not mutually exclusive. In practice, you can sum some layers, stack others, or combine techniques depending on the model and the goal. Summing means combining models by adding their parameters. It is simple, but it can still work surprisingly well, especially when the models are related. The basic idea is to take the parameter values from the models and combine them arithmetically. In practice, you often use a linear average or related interpolation method, and you may rescale models first if their parameter ranges differ too much. A linear combination is the most straightforward summing method. It includes a plain average as well as a weighted average, where you can control how much each model contributes. This formula says that the merged model is a weighted blend of the two models. The weights let you bias the result toward one model or the other. Read this as a normalized weighted average. If both weights are equal, the merged result is just the ordinary average of the two models. This example shows the simplest case where both models contribute equally. The important idea is that parameter averaging can produce a useful merged model without any extra inference cost. Here the layers are being averaged directly. That visual is important because it shows that merging can happen at the parameter level, not only at the output level. This figure is the visual version of the averaging idea. It reinforces that two trained models can be collapsed into one by combining corresponding parameters. Despite how basic it looks, linear combination often works well in practice. It has been studied for a long time and is especially common in federated learning and other settings where model weights are naturally comparable. You can average entire models, as in model soups, or average only selected components, such as adapters. Averaging adapters is often the more practical choice when multiple models share the same base model. When models share a base model, the difference between the fine-tuned model and the base model can be treated as a task vector. That makes merging more interpretable because you are combining the learned task changes rather than the whole model blindly. Task vectors also let you do arithmetic, add capabilities, or subtract unwanted behaviors. That can even be used to reduce biases or remove specific skills from a model update. Linear combination is simplest when models have the same architecture and size. If they differ, you may need to project them into a shared dimension before averaging. Some methods try to align parameters first so matching features are averaged together. That can improve the result, but alignment itself is difficult, which is why simple averaging is still more common in practice. The next summing method is SLURP, which stands for spherical linear interpolation. It sounds more mathematical, but the intuition is still about moving between two model vectors in a controlled way. SLURP is another interpolation method for merging vectors. It is often used when you want a smoother path between 2 points on a sphere instead of a straight arithmetic blend. Before we continue, remember what interpolation means: estimating an in-between value from known endpoints. In merging, the endpoints are the source models, and the merged model is the in-between result. Linear averaging is one interpolation method, and SLURP is another. Both are ways to choose a point between two model representations. Think of each vector as a point on a sphere. SLURP follows the shortest path on that sphere, and the interpolation factor decides how close the merged vector is to either source model. One limitation is that SLURP is defined for two vectors, not many at once. If you want to merge more than two, you usually do it step by step, merging the result with the next vector. Notice the red arc? That is the path SLURP follows. The blue point marks the halfway merge, which makes the idea of interpolation visually concrete. This figure shows the geometry behind slurp. The main thing to notice is that the merged vector is not a simple straight average. It lies along the spherical path between the two endpoints. Now we get to a useful practical refinement. Before merging, you can remove parameters that matter very little. That often makes the merged model cleaner and less likely to interfere with itself. During fine-tuning, lots of parameters change only a little. Many of those small changes are redundant, meaning they do not contribute much to the final task performance. Ties merging showed that you can reset a large fraction of task vector parameters back to the base model with little loss. In other words, not every learned change is equally important for the task. The plot shows that performance can stay strong even after many parameters are removed. That supports the idea that pruning before merging can reduce interference without destroying the useful task signal. The key takeaway from the figure is that a small subset of task vector parameters can preserve most of the quality. That is exactly why pruning is such a useful step before merging. Those redundant parameters may be harmless in one model, but they can cause interference once several task vectors are combined. Methods like ties and dare prune first, then merge, and that often produces a better final model. The next family of methods works by taking whole layers from different models and placing them together. This is more structural than summing, and it can even create new architectures. With layer stacking, you might take early layers from one model and later layers from another. It is also called pass-through or frank-emerging, and the result usually needs more fine-tuning to work well. This example shows that layer stacking can produce a large, capable model by combining parts from two fine-tuned models. It is a concrete example of how structure-level merging can work in practice. Layer stacking is also useful for mixture of experts models. Instead of training everything from scratch, you could duplicate layers, add a router, and then train the system to send inputs to the best expert. The point here is that reuse matters. By starting from a pre-trained model, you can sometimes get better results than training a Mo from scratch, and that same idea has inspired agent-style systems as well. Notice the flow in the diagram. The pre-trained model is not discarded, it is repurposed. The router is the key component that decides which copy of a layer should handle each input. This figure makes the MO construction process easier to visualize. It shows how model reuse and routing combine to create a larger system from an existing checkpoint. Layer stacking also supports model upscaling, where the goal is to build a larger model with less effort than training one from scratch. If you have more hardware available later, stacking can help you grow the model you already own. One concrete upscaling method is depth-wise scaling. The idea is to duplicate and recombine layers in a way that increases depth while keeping the architecture workable for further training. First, start with the original pre-trained model as your base building block. Then make a second copy of that model. The duplication gives you two parallel versions of the same starting point to recombine. Next, merge selected layers by summing some of them and stacking the rest. The exact pattern is chosen so the final model has the target depth you want. This is the key scaling trick. Some layer pairs are collapsed into one, while the others remain separate. That is how the model grows in a controlled way instead of just getting duplicated blindly. After the structure is built, the model needs another training pass to recover and improve performance. The new, larger model is not finished yet. Further training adapts it to the target task, so the extra capacity turns into real performance. This figure walks through the full, depth-wise scaling pipeline. It is a good reminder that structure changes and fine-tuning usually work together. The screenshot shows the merged structure after layers have been reorganized. What matters is the sequence. Duplicate, combine selected layers, then fine-tune the result. This figure summarizes the depth-wise scaling idea in a concrete example. A 32-layer model is expanded to a 48-layer model by combining some layers and keeping others separate. The third approach is concatenation. Instead of blending or stacking values, you simply join components together and let the merged component grow in size. Concatenation increases the number of parameters by combining the parts end-to-end. 4 LoRa adapters, That means the merge adapter's rank is just the sum of the two ranks. This diagram shows the rank growing after concatenation. It is a simple rule. When you join two low-rank adapters, the result is a higher-rank adapter. The figure makes the rank increase easy to see. Concatenation is straightforward mathematically, but the trade-off is that the merged model gets larger instead of smaller. That size increase is why concatenation is often less attractive in deployment settings. It may improve performance, but if it does not reduce memory, the extra cost can outweigh the benefit. Now we shift from the theory of fine-tuning to the practical choices you make when you actually start training. The key question is not just whether to fine-tune, but how to do it efficiently and sensibly. The hard parts are usually data, deployment, and maintenance. The training loop itself is comparatively simple, so this section focuses on the decisions that matter most in practice. We'll start with the two biggest setup decisions: which model to begin with, and which tooling you'll use to train it. Those choices shape the rest of the workflow. At a high level, you only need to pick three things: a base model, a fine-tuning method, and a framework. Once those are set, the actual training plan becomes much easier to organize. Let's begin with the model you start from. In fine-tuning, the base model is often the single most important choice because it sets your ceiling for performance. A good rule is to begin with the strongest model you can afford, then test whether it can solve the task at all. If even that model fails, smaller models are unlikely to help. If it works, you can use it as a benchmark for cheaper options. Fine-tuning often follows one of two paths: progression or distillation. The difference is whether you're first testing, then scaling down, or first extracting quality from a strong model and then transferring it to a cheaper one. First, let's look at the progression path. This is a practical way to move from debugging to validation to full comparison across models. The first step is simply to get the training pipeline working. Before worrying about model quality, make sure the code runs cleanly and produces the expected behavior. Start with the smallest and fastest model that is cheap to run. This is a debugging step. You're checking that the fine-tuning code itself behaves correctly before paying for bigger experiments. Once the pipeline is stable, move to a more representative model. At this stage, the point is to test whether your data really teaches the model something useful. A mid-tier model is a good checkpoint for data quality. If the loss does not improve as you add data, that is a warning sign that the dataset or setup may be flawed. After that, you can focus on the best performing model. This is where you try to squeeze out the last bit of quality once the setup is known to work. Now, run a few careful experiments with the strongest model. The goal is to see the upper end of performance, not to change too many variables at once. The final step is to compare all candidates under the same conditions. That gives you a realistic view of cost versus quality. Once results are good, train across the full set of models and compare them directly. That lets you choose the option that best balances cost, speed, and accuracy for your use case. The second path is distillation, where a strong model helps create the data for a smaller one. This is useful when you want quality first, then efficiency. The first stage is to get a strong model to perform well on a small amount of data. Because the model is already capable, you often need less data to reach good quality. Start with the strongest model you can afford and a small dataset. The idea is to produce a high-quality teacher model with as little data as needed. Next, use that teacher to expand your training set. This is where the model starts helping you scale the project. Use the fine-tune model to create additional labeled examples or better training targets. That turns a small starting set into something much more useful. Finally, take the larger dataset and train a cheaper model. At that point, the goal is to transfer the quality you discovered into something less expensive to serve. With the expanded dataset, you could train a smaller model that is more economical to deploy. This is the main payoff of the distillation path. Because fine-tuning usually comes after prompt experiments, you should already know a lot about model behavior by this point. Use that knowledge to choose a development path instead of starting blindly. Now we turn to the choice of method. Here the trade-off is usually between cost, data efficiency, and the maximum quality you can reach. Adapter methods like LoRA are a good starting point because they are cheaper and easier to manage. If you later need more quality and more control, you can move on to full fine-tuning. Data volume matters a lot here. Full fine-tuning usually needs thousands of examples or more, while PEFT methods can work well with much smaller datasets, sometimes even a few hundred examples. You also need to think about deployment. If many fine-tuned versions share one base model, adapter methods are easier to serve because you keep one shared model and swap adapters instead of hosting multiple full models. The next decision is tooling. Some teams want the simplest possible path, while others need maximum control over training and deployment. A fine-tuning API is the quickest route. Upload data, choose a base model, and receive a trained model back. The trade-off is flexibility, since you can only use the models and settings the API exposes. If you want more control, use a framework such as LLM Factory, Unsloth, PEFT, Axolotl, or LitGPT. These tools support many fine-tuning methods, and for full fine-tuning you can often use the model author's own training code. Doing the training yourself gives you more flexibility, but it also means you must provide the compute. For adapter-based methods, a mid-range GPU may be enough. For larger setups, cloud integration becomes important. If training spans more than one machine, you need distributed training support. Frameworks like DeepSpeed, PyTorch Distributed, and Colossal AI help coordinate that kind of workload. Once the setup is chosen, the next layer of decisions is tuning the training behavior itself. A few hyperparameters show up again and again because they strongly affect stability and quality. The exact best settings depend on the model and the framework, so always check their documentation. Here, we'll focus on the hyperparameters that most often matter in practice. We'll start with the learning rate, because it is one of the most sensitive controls in training. Too much or too little can easily make the run ineffective. Think of the learning rate as the size of each step toward the solution. Small steps can be slow, but large steps can overshoot and prevent convergence. There's no single correct learning rate. A common approach is to search a reasonable range and often start from the pre-training learning rate, scaled down by a factor between 0.1 and 1. The loss curve gives you practical feedback. If it jumps around, the learning rate is probably too high. If it falls very slowly, it may be too low. You can also vary the learning rate during training. Schedules often use larger steps early on and smaller steps near the end to keep training stable. Next is batch size, which controls how many examples contribute to each update. This affects both training stability and memory use. Very small batches can make training noisy and unstable, while larger batches usually produce more reliable updates. The trade-off is that bigger batches need more memory. In general, larger batches let you process training data more efficiently, but hardware limits usually decide how far you can go. That is why batch size is often constrained by available GPU memory. This is one of the clearest trade-offs in fine-tuning. Better hardware can buy you faster and more stable training. But if compute is expensive, you may need to settle for smaller batches. When memory is tight, gradient accumulation helps. Instead of updating after every small batch, you collect gradients from several batches and update once, which makes training behave like it used a larger batch. If compute is not the main constraint, try different batch sizes and compare results. Sometimes the best batch size is simply the one that gives the most stable learning on your data. Now, let's look at epochs, which control how many times the model sees the full dataset. This is a simple setting, but it has a big effect on overfitting and underfitting. An epoch means one pass over the training set. More epochs mean each example influences the model more times. Smaller datasets often benefit from more passes through the data, while huge datasets may need only a few. The right number depends on how quickly the model is still improving. The training and validation curves tell you whether more epochs will help. If training improves, but validation gets worse, the model is overfitting and you should usually stop earlier. For instruction fine-tuning, not every token should matter equally. The next hyperparameter helps decide how much the model should learn from the prompt versus the response. During training, both the prompt and the response can contribute to loss. But at inference time, the user supplies the prompt, so the model should be trained to focus more heavily on generating good responses. That is why prompt loss weight controls how much prompts count relative to responses. A typical default is around 10%, which keeps some signal from the prompt while still emphasizing the answer. Let's wrap up the fine-tuning chapter with the main ideas in one place. The goal here is to separate what is conceptually important from what is operationally easy. This chapter was hard to organize because fine-tuning connects older ideas like transfer learning with newer ones like PEFT, plus theory, memory math, and practical tuning. That mix is exactly why the topic needs a careful structure. The actual training loop is often the easy part. Modern frameworks automate much of it and even suggest common methods with reasonable default settings. What takes judgment is deciding whether fine-tuning is the right choice at all. That includes the broader trade-off with RAG, so the chapters start from the decision, not just the technique. In the early days, fine-tuning meant updating every weight just like pre-training. But as models grew, the memory, time, and data costs made full fine-tuning impractical for most people. Most newer techniques are trying to solve the same problem. Keep performance strong while using far fewer resources. PEFT reduces trainable parameters, while quantized training reduces how many bits each value needs. LoRA is one of the best-known PFT methods because it is parameter efficient, data efficient, and easy to deploy. Its modularity also makes it easier to serve and combine multiple adaptive models. From there, the chapter moved to model merging, combining multiple fine-tuned models into one stronger model. That idea shows up in practical settings like edge deployment and model upscaling. A common reality is that fine-tuning itself is manageable, but good training data is not. High-quality annotated data, especially instruction data, is the harder problem, and that is where the next chapter goes. Some people call the cost of making a model behave better an alignment tax. The term is useful, but it can be confused with other alignment-related penalties, so the wording needs care. In practice, many organizations keep using technologies that are already acceptable, even if better options exist. Switching only makes sense when the improvement clearly outweighs the disruption. Sometimes engineers want to fine-tune mainly to learn the skill, not because the project truly needs it. That is perfectly understandable, but it becomes an important distinction when you're making decisions for a team. The date in a model label can matter a lot because different releases may perform very differently. When you evaluate a model, always pay attention to which version you are actually using. One school of thought says post-training should help the model express what it already knows, rather than add lots of new facts. That framing is useful when you think about the limits of fine-tuning. Backpropagation is dominant, but it is not the only way to train networks. Evolution strategies and direct feedback alignment are examples of other approaches worth knowing about. If a parameter is not trainable, you do not update it, and you do not need its gradient. That simple rule is one of the main ways fine-tuning saves memory and computation. Everyone eventually meets the CUDA out-of-memory error. It is a reminder that memory is often the real constraint, not the idea of fine-tuning itself. If you want to go deeper on inference memory, this is the kind of arithmetic that helps you predict limits before you hit them. It is especially useful when comparing deployment options. Training memory is a separate problem from inference memory, and it is usually more demanding. A dedicated memory breakdown helps you understand where the cost comes from. bfloat16 is a widely used format because it can deliver strong performance on TPU hardware. It is one of the key numerical formats to know in modern training systems. Integer-based numerical formats are often described as fixed-point formats. That name helps connect them to the broader idea of representing numbers with limited bits. In floating-point formats, some bits control range and others control precision. The range bits are the exponent, and the precision bits are the significand. Format names can be misleading. TF32 is labeled like a 32-bit type, but its actual bit structure is different, and the name mostly signals compatibility with FP32 behavior. Even experienced practitioners can mix up FP16 and BF16, especially when comparing model releases and hardware support. The broader lesson is that numerical format details matter more than the label suggests. Designing numerical formats is really about finding the lowest precision that still preserves quality. When that works, the result can be much cheaper, faster, and more deployable. Model weights are not the only memory cost. For transformer inference, the KV cache can be a major contributor, and it deserves separate attention. It is interesting that the IEEE rules still allow extremely small floating point formats. That shows how much flexibility there is in number representation. Model compression is not just an academic idea. It can lead to real companies and real products. This is a good reminder that efficiency work can have major practical value. During training, tiny numerical errors can build up over many steps. That is why precision matters, both for stable optimization and for getting the loss value right. Mixed precision training is a practical answer to the memory and speed problem. The fact that large teams rely on it shows how central it has become. In partial fine-tuning, people often update layers near the output first. Those layers usually carry more task-specific information, while earlier layers stay more general. A lot of fine-tuning methods sound similar, but they differ in what they update and how much memory they need. That is why it helps to compare them by mechanism, not just by name. To use LoRa well, you need to know how the target model is built. The exact weight structure determines where the adapters fit and how they should be applied. Some tools cap the LoRa rank, but that limit is often about available memory rather than theory. In other words, the software constraint may reflect hardware reality. If you're searching for ready-made adapters, the naming clues are often simple. Tags like adapter, PEFT, or LoRa are the most useful filters. QLoRA is important, but it is not the only quantized LoRa variant. There is broader research activity here than what is publicly visible. The broader systems view of machine learning includes both cloud and edge deployment. Fine-tuning decisions often depend on where the model will actually run. Ensemble methods are another reminder that combining models can outperform a single model. The same intuition also appears in fine-tuning and merging techniques. Averaging is one of those simple ideas that keeps showing up in machine learning. Used carefully, it can turn many small pieces into a useful single representation or prediction. One useful assumption in model merging is that the weights that change the most may be the most important for the target task. That gives you a way to reason about which updates to keep. The chapter also covered specific merge methods like ties and dare. The names are quirky, but the underlying idea is to manipulate task vectors in structured ways. Here, pruning is not about making the final model smaller. It is used to sparsify task vectors so the merge works better. Not every technique in the chapter is equally central, but some are worth mentioning for completeness. Concatenation is one of those methods. This is the kind of failure everyone learns from once. A long training run can be lost because the checkpoint path is wrong. It is a simple mistake with expensive consequences. Small batch sizes often make training noisier, but the exact reason is not always easy to pin down. The important point is that batch size can affect stability as much as speed. Gradient accumulation helps simulate larger batches without storing everything at once. Its history is tied to distributed training, where gradients from multiple workers are combined before an update.